Namash and Simone Chiarello. And this is about the cohomology of the moduli space of Higgs bundles. So just very quickly, I remind you what the objects are pursued in this conference. These are well known. So we will look at a Riemann surface sigma. I'll fix some line bundle from degree 1 on it, or any odd degree, and we introduce our two usual spaces. So the space n, which is the space of stable bundles. So we look at some rank 2 bundle whose determinant line is this psi. That's why we fixed it, and then we fixed the usual stability condition. Means that for any subline bundle, I'll just look at the rank 2 case. Subline bundle has a degree less than half of the degree of V, which is now one side. 0. So this is the moduli space of stable bundles, and then there is the moduli space of Higgs bundles, which looks like this. So we do the same thing. Also rank 2, so this actually is repeated. And then we have another object phi, which is just an endomorphism with V twisted by the canonical bundle. So if you look at this SL2 case, then I'll fix trace by 0. And then the stability condition is slightly modified. So we say that we only impose this on invariant subbundles. So these are our two spaces, and what we'd like to understand is the cohomology of these spaces. And so I'll set up some language for this. Yeah, maybe just one in already. I'll put this down. These are the space. I apologize. So, I mean, there's these two spaces, of course, are related. And one thing that will be important for us is that there is a torus action here, a C star action, and one can look at the fixed point set of this, and the fixed point set looks like as follows. So clearly, when phi is 0, then if phi is 0, then any line bundle is invariant, and so then we just reduce to the previous condition. And so we see that M is, if we look at the fixed locus of M, then this is just, we'll have several components. One of them is N, and as I said, this is the case when phi is equal to 0. And then the other is, there are some other components. This is a disjoint union of several smooth components. The case is when precisely use phi to stabilize a vector bundle that otherwise would not be stable, and those are the cases when V is L1 greater than L2. Okay. So I'll use this a little later. Now for the, so it'll be lots of formulas in today's. So let's just set this up. So the way to think about this homology ring is the following. We look at the universal bundle on, say, on M, but the same thing, of course, then works for N as well. And then what we do is let's look at lambda 1 and lambda 2. So these will be the churn roots of this rank 2 universal bundle on the product, and then we introduce Y, which is the difference of these, and this is now rank 2 churn root on M. And we do this in particular because this U is not well defined and then this difference is well defined. So this Y gives you a well defined Chern root on M, which means that in particular that so if I take Y squared, that it actually becomes a cohomology class on M cross sigma. And then to produce classes now on M, we cap the class of is polynomial one variable Y by the homology classes of sigma. So let me write this down. So the idea is the following: we'll look at some say T, which is a polynomial now in as I said in the Y squared, so it's Y, or it's invariant polynomials in Y under the change of Y to minus Y. So we look at a polynomial like this. So this gives us a cohomology class in H star of M cross sigma, just by taking the corresponding invariant class. And then now we take a class eta in the homology of the Riemann surface. And so actually in this talk, I'm mainly just interested in the two obvious classes. So there will be the class of the point and the class of sigma. So these are, so I'll not put the brackets around it, I should, but okay, so these are the two interesting classes. As examples of these etas. Anyway, if I have this eta, then I can now, from this I can cap this, and I introduce this class T eta, which is just, the class corresponding, let me just deal with this map by mu for a second. So I'll just look at this mu of T, and then I cap it with the class eta, which is in this. Okay, and now this gives me a class in the homology of M. Okay, so now there is, I'll look at all classes generated by this construction, and so what I get is the following. So I'll get a ring R, which is then just looks like this. I'll take this now polynomials. So I'll take Y squared, and so Y first, and then I cap it with a point, so that's one class, and I can take powers of that. And then I can also take Y squared and cap it with sigma, so that's another class. But of course, so this notation is multiplicative when it's a point, but it's not multiplicative when you take a cap with sigma. So in principle, then I have to take Y to the fourth, sigma, etc. So it's, in a sense, it's a ring of infinitely many variables, but in reality, it's easy to check. It's an easy exercise to check that, in fact, it is already generated by the first three elements. So we'll actually concentrate on these three elements. And now, this ring defines maps onto the cohomology of M, and so there is some technical details which I'll omit now, which is that there's what I will call the interesting part of cohomology, and so I'll denote it by homology hat. In any case, I look at the image, the surjective image of these classes, and that's what we're interested in here. But this essentially contains all the interesting information for us.
So are these classes the alpha, beta, gamma?
Yes, these are sort of alpha, beta, gamma. I mean, alpha, beta, gamma. I think it's some gamma plus alpha, beta. Yeah, or something. Okay. So I'll not use that notation. And so, by the way, you can go on then to the homology of M. So as you can see, N is actually a subset of M. So this is a meaningful. Okay. So next, I will Okay. So next I'll try to explain. So our purpose is to understand this map, understand this ring, understand the ideal, if you like, of these relations. So this is sort of the purpose of the game in general. So next I'll discuss now the perversity. Reverse filtration. So the perverse filtration is studying this cohomology as relative to the corresponding Pidgeon map. So we look at this map M maps onto the. So if I take the determinant of phi, then it maps onto the sections of the square of the canonical bundle, which is a 3G minus 3-dimensional space, and this is a 6G minus 6-dimensional space. And we are interested in, actually there is something you can say about homology. It's kind of subtle and it's not completely enumerative. What you can say, what you can do is the following. So what you can do is that you can look at, say you look at the yi, it's dim I, so this is a linear space, of course. So this is just a dimension, so this is just isomorphic to C 3G minus 3. So I'll look at maybe Fi linear subspace of this gamma k squared. And then what I can do is I can look at the image, the inverse image of this thing here, and look at which classes have support in that inverse image. So this perverse filtration has this formula. So it will be P handwritten using Poincaré's convention, and pk minus I minus 1 of some class alpha is going to be the is just equal to the right. So I'm not going to use this form. This is a usual formulation. So this is the kernel of hk of m. This map of hk of this determinant of phi inverse of yi, or y is somehow generic. Okay, so what we're measuring is the support of homology classes, and that gives you a new filtration on this H. So this is exactly what. So as I said, this is not really enumerative. It measures it has some geometric flavor. So the first step that I'd like to discuss is to give a sort of an enumerative sort of version of this. And this is the following. It's based on results of Di Cataldo and Migliorini, and it goes as follows. So here, so we will introduce an auxiliary space where we can do the enumeration, and that's the space Z. So what I'll do is I'll take Z, and I will choose an M line bundle, and you divide M by, take the geometric invariant quotient with respect to that torus action over there. Okay, so then this is now a projective orbifold of dimension 6G minus 7. Okay, because M was 6G minus 6 dimensional, now this is 6G minus 7. And so now it turns out that, so this whole thing goes through. We have this diagram now. I have this map M into Z, so this is a projective map, of course. And then there's a corresponding Hitchin map, gamma k squared, and there's of course the map P gamma k squared. So this is now 3D 4-dimensional projective space with the obvious rational map like this. And so now let's just look at the cohomology situation. So
is there like a parameter there? Is there like a parameter? I mean, what sort of linearization are you taking for T?
yeah, so there's sort of a unique quotient in this case. I mean, if you choose the correct.
It's the highest.
It's the highest one. You want to include all of the...
Yeah, you want to have all of
variables.
those.
Yeah.
Okay. So first, So one thing is then here. Well, maybe not too late now, so I'll just repeat that. So when I have this map, of course, now I have an actually honest class, which is that, so U will be an element of H2, of course, of this. And so I can just pull this back and build an obvious element denoted by the same way in H2 of Z as well. And together, now the following things are true. So together with this U and all the other classes that also descend, I'll have now, because there is the, so now, maybe one thing that I missed here is that I can now, this picture, let's denote this maybe by tau. This picture I can now do everything in the equivariant setting. So there is this. And say that this works. So this also in the equivariant setting. So this T equivariant, so all the bundles, this universal bundle is T equivariant, and so then you can just look at, put HT here, and then the one thing you need to change is that, I apologize for writing the formula, is you just use this RU where you adjoin this variable U, which is the generator of H2 of BT. So H2 of BT is equal to UU. Okay, so the whole thing works in equivariantly, and then we can use Kerman's, the Kerman map. So we use H equivariant now of M maps onto the usual cohomology of C. And this is what we're going to use. And then that U precisely goes into this U. So these U's are all the same. Okay, so this is the program. It's rejected. And then I can formulate sort of a set of statements. Let me call this theorem. Which, well, it's a bunch of things. So it's Kalkman, Jeffrey Kerwin, Witten, and maybe some others. But so this is the following statements. They imply the following statements. So one is that this RU, and Markman also, sorry. So one statement is that this RU, so this ring with all those tautological classes attached to plus U, which map one to Z. So this one is a surjection onto this H of Z. Again, there is some homology, of the interesting homology of Z. So this is surjective. The second is a calculation. So now this is a compact orbital. So I can finally integrate, and that's what I call enumeration, right? So you can integrate things. So we'll look at some object P hat, a P bar in this RU. I'm trying to make the notation somewhat consistent, but probably it's not going to work. But so in any case, so there are some things that I call T, which which are just polynomials, so with capital letters. And now there are some elements hatted, which are in this R, yeah. So they're slightly different. Polynomials, they're all in the substance.
So is the first line a definition?
Pardon?
Is the first line a definition?
No.
I mean, what is H star hat of Z?
No, so I didn't tell them. So I said from the very beginning, every H has a hat on it. And that just means that something I'm not explaining. But it's the invariant homology. So for example, I can say what it is. It's you basically get rid of two things. One is that you look at the symplectic invariance only. Yeah, the symplectic group, symplectic G acts on the homology. You only look at the invariant part, and you also only look at the part in which the torsion points act trivially. So enumeratively, this is what you see. So that's why I call H hat. But so I'm not explaining this.
Maybe it's just the invariant.
It's the gamma invariant part, right? It's the gamma 2 invariant part. It's the gamma 2 invariant part.
Yes, but I think the two together may just be.
Maybe that's the same thing as invariant of the mathematical. Exactly. So that's another way of saying it. Okay. So it's meaningful now to ask what is the integral of a z of p hat. And the statement is, this is Kaufman's theorem, that this is just the residue at u equals 0 of the equivariant integral of p hat, now interpreted in this other way. So this u has two meanings. One is on m and one is on z. P hat on m. Okay, so this is the first, this is Kaufman's theorem. And then the next thing is essentially a definition of what that integral m p hat is, the equivariant integral. So this is really a definition. And this is just it's a sum over all the components of the fixed point set under this t action, and then you have the usual localization formula. So this is the close. The integral of, so you look at this, whatever, tau hat, so this homology class restricted onto the fixed point component, and then divided by the equivariant Euler class of the normal bundle of the component. Okay, so this is the usual about localization. And so finally, what's important for us is the following: is also that hat m is equal to h z divided by u, which is also in some sense. Well, this requires some extra knowledge also of the situation, but this is not so difficult. Okay, so what the upshot is that finally, so what we remember, what we wanted to understand is this map, in fact, this surjective map. We wanted to understand this ring, and the claim is that what we can understand this by calculating usual intersection numbers on Z, which is a compact manifold, and the way and for Z, we do have a formula in terms of the fixed point sets. So those C's are those N and F that you find out. Those fixed point sets via some integrals that are calculable, because in this case these fixed point sets can be identified. Okay, and so just there's this mysterious division by U. So I want to explain a little bit what that means, because this is actually looks simple, but it's not at all simple. So actually, just before I have a little space here, maybe I'll explain what I mean by this equivariant integral, this formula. Maybe I'll just explain this formula. So it's the simplest. No, I'll do it here. So just a little example for equivariant integration of Kaufman's formula. Kaufman's formula. And this is the, say, just really a trivial example. For example, you take C and you add by this C star on it, by this torus, and then the quotient, the geometric variance is just the point, of course. Okay, so then you want to integrate the function 1 and the points, you should get 1. So then you just look at the residue at u equals 0, so there's a du somewhere there I should add. So what you do, you restrict this 1 to the fixed point, which is 0, so then you just get 1. And then you look at the normal Euler class that's just weight 1, so it's just u du, and you just integrate this over at the point 0, and so that's just this value, and the residue is just 1. The residue is 4. So you recover the integral at point 1 is 1. Okay, so this is the general scheme. What you're doing, and this more general, more difficult formula works the same way. Well, I'll tell you what the results that you get. Okay, so now to explain, going back, another remark about this, I would like to explain still what this means, because this is, so what this means is the following. So this last equation means the following, is that, so we look at some Q now in R, okay, so in this range. Let's do without the U now, so there's no U. And I want to understand when it is in the ideal. So for example, so I would like to say that then tau Q is 0, so it's Q is in the ideal of those relations, if and only if there exists an F hat now in RU such that this is an equivariant extension of Q. So what this means is that if I integrate take Q and add U times F hat to it and multiply it by arbitrary P hat, then you get 0 for every P hat. Okay. So this is just a trivial. Rewriting of Poincare duality. Of course, if you have it's a compact orbifold, doesn't matter, smooth manifold, then to say that a class is 0 precisely means that its multiplication is 0 by every class. So this is just sort of a triviality. But now you see, but obviously then if this is true, then Q is equivalent to F hat, U times F hat, so it will fall into this kernel. So this precisely, this is what this says. But this shows that computation, this will be pretty difficult, right? Because, so to determine if something is a relation, you have to find this equivariant extension of that relation via this incredibly not so simple formula, and so of course that's not so simple. So, but this is the meaning of that. Okay, so I still haven't talked about perversity, so let's talk about this perversity. It's fairly easy to write it down now in this form. So this perversity becomes enumerative in Z, so that's the first observation that goes back to the Cataldo and Lugarini. So this definition, proposition, if you like, so for me it's going to be the definition, but actually I mean it's not so, I don't think this is very so deep. But so it says the following thing, that some class, say Q, is in the, so now of course I mean tau Q is in the ith perverse, whatever, filtrum, if and only if And so I write down something very similar to this, but now it'll be just twisted by power of u. So it just says that there exists an f tilde, f bar, sorry, such that the integral of, and so I still have the same thing actually, q plus u f bar p bar is 0 for every p. The only thing is that I'm going to twist here with the power of u, so and that's u to the power 3g minus 3, and then there is this difference, so it's the homological degree of q minus the perverse degree of q. Okay, and so anyway, this is some formula, but the point is that it's not very, very surprising, because remember, this perversity was defined by some inverse, by linear subspaces coming from the base, and this u represents the hyperplane class of the linear spaces in the base, and you just multiply by there's some numerology here by the powers, but obviously these two things are very closely related, so there is not so it's not so different. Right, so again, these bars I'm writing because the q has no u in it, and the ones that have bars have u. That's why they have differentiation. Okay. So this is the definition, and so then now what is the, I can write it down now, what is the P equals W conjecture, which is in this case, well, let me write it down. So this is the form I like very much, because what you can see, I mean, one very easy way to see what we're talking about is that if you look at this ring, now this has now an obvious grade, well, it has two obvious gradings. So one obvious grading is that is the homological grading. So let me just make a remark. So gradings. So obviously the degree of y to this, say, 2k eta is just equal to so y has degree 2, so it has 4k minus the homological degree. All right, just remember this, homological of eta, right? I mean, that's obvious. And obviously this gives a grading, because I mean, that's consistent with homology. But the point is that if you look at that, there is a primitive stupid grading also on this ring, which is just the degree of y, right? So that's also a grading. The other is the degree of y. So I mean, it's simply that the degree of y to the 2k eta is equal to just whatever, 2k, 4k, it doesn't matter. Okay, and this is actually the perverse degree. So we would like to show that this degree is the perverse degree. And so the P equals W conjecture, well, actually I will not really use the weight filtration, I make a comment here. But it just says that the perverse filtration and the claim that the perverse claim is that the perverse filtration gives rise to this the stupid grading, to the whatever degree in y, the second grade. So in particular, it's multiplicative. So it's called P equals W because there's some people sense where one can look at the weight filtration in the other hyperkähler sister of this space, and there it gives a weight filtration that's known to be multiplicative. So in fact, if one proves this, since this is of course multiplicative, if one proves this, now one proves that this perverse filtration is also multiplicative, and that will mean that the two are the same. because W is multiplicated by the least one. So in any case, this is not so, this part is not so crucial for us. I mean, we simply want to prove this very, I think, very elegant kind of statement. Okay, and so this is not very clear. So, for example, just an example of this equality. So you want to prove something, things like this. So you have, for example, you take the class y 2k point, and you want to prove that there exists, you want to find a polynomial in those things with u's and all the other y's, such that that this is equal to 0 for any p, and you're looking for the f. Okay, so finally, this is the enumerative, and finally the enumerative version of the perversity.
Sorry, there is also the multiplication by u.
Sorry, I forgot the most important thing. Yeah, that's why I wrote it down, but I forgot. So it's u to the power 3g minus 3 minus 2k in this case, to calculate that definition. I mean, if you compare, now you can just find this coefficient, I just give you this example of that.
But is there a per equals W for the other part, but not the hat part?
Yeah. So the other ones should be, yes.
Is that easier to prove or something like that?
It's after this, it's not difficult to prove, yes. Okay. I mean, because particularly, so there's the odd classes. Actually, I don't know what happens with the non-variant homology. I don't understand that. I only understand this variant one. There's, of course, then there's just the symplectic action, and so then you just have these odd classes, the degree 3 classes, when you calculate the one cycles, and they multiply to these ones. So they kind of come back to these anything. So that's not so difficult. Okay. So now, a new story. So this is a setup, really. And so now, I would like to write down the actual formulas. So obviously everything goes through this thing. So finally you need to understand these things, because these formulas. So I'm going to write down this formula. So the first result, so now integration formulas. Oh sorry, so I didn't say the most important thing here. Just stop going back 1 second. So this is, so the plane, sorry. This is plane by, yeah, I didn't say the most important thing. So plane, so this is the B equals W conjecture. And of course, I need to mention that this has been proved by Hausel, De Cataldo, Hausel, Miolini. This is somewhat different methods. So this is another approach, which, as you can say at the end, gets almost the same result. So, so this, I'm proving a theorem that's already been proved, but I'm really hoping that this will also hold a higher rank than I'm explaining now. So this claim has been proved before us. Okay, going back. So now I'm doing the integration formulas. So the form now I write something really incredibly, well, looking involved. So that's the following. So now I write down a formula for the equivariant integral on M, so that thing there, M, and so I take two polynomials now, T and S. And T and S will be, I write it here just in this, just functions of y, and y can be thought of as a linear parameter coordinate on the Cartan and the corresponding to S. I'll do that, this is how it generalizes rank, but in any case. So I look at this class, and exponential, this is some physics thing that is not clear actually to me, but anyway, this is what you need to do. Okay? This is the thing that has a nice formula, and the nice formula, well, it's moderately nice. So this is equal to the following. So before I write it down, I write down I write it down here. Following thing. So I'll write a little formula here. Omega equals the following: 2 to the 2g minus 2 ty. Hope it fits. U squared minus y squared times s double prime, and then minus 2u to the power g. That's the numerator, and then so there is a second derivative of s, and just ty is just enters multiplicatively, and down you have u to the g minus 1 times the hyperbolic sine of s prime times u minus hyperbolic tangent of s prime over 2, and then it's not over, so I continue the denominator times u minus hyperbolic cotangent of s prime over 2 times the usual y to the 2g minus 2 and u squared minus y squared to the 2g minus 2. So, and I'll multiply this by d. So this thing here multiplies the denominator. So the denominator, that's the numerator. So you write down a differential form. You think of this as a differential form on C. So in the parameter, sorry, dy. So a differential form in the y plane. And yeah, it looks pretty ugly. In any case, that's what you get. And so the claim now is the following: that this is equal to the residue. So this is a different residue now. That was a u residue. Now I'm talking about a y residue. So this is new. So this has a bunch of poles. So in y, it has a pole at least here and here. So here you can see it's 0 and plus minus u. So it equals to the residue at y equals 0 plus the residue at y equals plus minus u of omega. Okay, so that's the And so the beautiful thing we discovered like ages ago, many of you weren't born yet, probably with Tamás, is the following fact that in fact there is some intrinsic meaning to this differential form, because this one is actually equals to the contribution of n. So remember, this equivariant integral is a sum somewhere here. This equivariant integral is a sum over the components of the fixed point set which are listed there. So there's at least this n and this f. So this is the contribution of n, and this is the contribution of f. So I don't know what this means in physics, but in any case, to the integral. Okay, so there's some kind of intrinsic meaning to this omega. Okay. So this is sort of a first remark formula that you calculate using fixed point using that formula that's given you. Just do it explicitly, what's written there. Okay, and so now
So this doesn't see the fact that f has a different component.
yes, it does have cheating. No, you have to actually. It's very well. Otherwise, this would be too trivial. So what happens is that actually f has g minus 1 components, and then you write them out separately. And there's a geometric series that comes out that you can sum. And when you sum them, then it's a sum of this. So I wrote f, but it's actually the sum of all those components. Really, it's not just valid. It's meaningless to write f. You have to do separately because they have different dimensions. Yeah. I don't know if that's actually visible up there.
So then what's the significance of the plus and the minus? Do the residue
That's
sort of break
no,
each
that's
other,
the
or-
same. It's symmetric. So no, it's a sum of the two. I mean, it's a sum of plus and minus, but they are the same. So there is no relevance. Okay. And so I have maybe 10 minutes. Okay. And so now I will get to this interesting part. So So there is some very beautiful thing that I like very much that I've done several times in my career is that okay, and you remember now that so I have this thing. So then as what follows is that the integral of the corresponding thing t pt x s sigma over z, thus according to the formula. So there is just the residue at u equals 0 of the residue at y equals 0. So this is not something totally elementary. So even if you didn't understand anything more, this is the residue y equals plus minus u of omega, right? Because the Kalman series said I just have to take the residue of this to calculate. Okay. And so the point is that there is some sort of hyperplane arrangement. There's various ways of looking at it, but the point is that you can change the order of integration. You write down the residue as a double integral, use Fubini's term, and you can change first integrate with respect to u, and then integrate with respect to y. And if you do that, then you discover that this is the same thing as the residue with respect to y equals 0 at times of the residue, and then now in u we'll have a residue at u equals 0, and plus the residue, so there's du. The residue, and now a mysterious pole appears that wasn't there before. That happens usually when you change the order of the residues, and this is what I call this mysterious data pole. So this is at u equals to that root over there, the hyperbolic tangent of S. Okay. And now just a quick remark. A quick thing is that, yes, so this is it then, in principle. This could help, and it does help a lot, because you see there's a very large part of u here. So what happens is that for our case, for example, when we have something like this p hat, which replaces this whole thing, remember, which is, for example, this thing, u3g minus 3 minus 2k times beta plus, oh sorry, y to the 2k point. So what you have there, actually, I'm just copying, minus uf bar p, whatever, so I used the wrong thing here, sorry. Bar, so if you, when you have this has a big power of u in front of it, and that actually kills there's a u to the g minus 1, but that kills that part. So in this case, the first term disappears, and you just have the residue at y equals 0, and then this pole is simple. Simple pole. So that means just a substitution. So you just have omega with the substitution u equals to this thing. So this was pretty awful, and so now it's an order of magnitude less awful. What you had before, you have a simple pole, it's localized now also. That's what's special about this. Some of the problems, either way you look at it, this thing is somehow not local, this formula. I mean, you have something at 0, but here you have something at 2 different points. That makes it more difficult to calculate. And here, the same thing, if you do u, you also are at 2 different points, but that's kind of infinitely difficult to handle. But in this p equals w situation, integrals that you look, they are somewhat special, they have these powers, and that means that one of the terms is actually killed, and so you're only left with the other one, and that's something that you can theoretically calculate. I say theoretically because I tried to do it for several years, and I actually couldn't find this f tilde, but I mean, this is at least computer-wise, etc., was doable. And so then, there's with Simone, finally, we found the solution, and so the solution is the following. So now, okay. So again, what we need to show is, so we here, where am I? Here. So I have this expression, and what we need to show is the existence of an f, such that this integral m is 0 for every p, right? So that's the statement. So I'm going to explain a little bit. Of course, this is now really a calculation. It's technical, so just explain some little details about it. this allows a reasonable calculation, this observation about the vanishing of the other pole. So I just give some pointers in this last 5 minutes of what this involves. And so the first pointer. So this is the base. So yeah. So what you find in the denominator, so this u equals hyperbolic and u equals hyperbolic, is the beta Andras equation. Of course, so now it's cheating. It looks very simple, but actually, of course, the real thing is that it should be y expressed in u and u expressed in y. So usually usually we say that beta Andras equations, this y cannot be solved. But actually, just for rank 2, they can be solved in reverse. U can be expressed. It is a factorization. And so that's the solutions over there. So those are the two solutions. Hyperbolic and have a cotangent. And if you look, the special thing is that sorry, I made this there actually, but I made this small thing. This line here. Sorry. Oh, there's a line. And here. Yeah. So that changes why it's important, because then you can see that u is over order of y squared there, because s prime is approximately y. And in the other guy, u is just a constant. So that's why this tangent is different. That's why it's important. So you have this a special clause, you use y squared, and that's why this appears in this when you change the integration. So that order is actually is very important. So, and this is my problem that I don't know, and apparently I don't know how to solve, even in a reverse sense, the beta Andras equations for higher rank. That becomes apparently that's not so simple. So physicists tell me. Okay, so let me just finish this now with just maybe 5 minutes by some observation. So the first thing is how this calculation. I just take 2 little bits. So yes, so we found this solution, and that. So the first observation, this localization, what it tells you is that you can look at the classes of as the orders of our variables, which are those y's and this u, at this point y equals 0. So this gives us, so this localization, I can call it localization, gives rise to a sort of a new grading, which allows us to calculate to organize our calculation. So because since we are calculating vanishing of things, so obviously if the order of y is positive, then the residue is 0. So and this is the following. So you have u, you have y squared sigma, these are alpha, y squared point, this is beta, and y, the fourth sigma, this is gamma, plus something. So this is the cohomological degree. Cohomological degree is, of course, this is just 2, 4, and 6. And then there is this, the y pole degree, or y power, or whatever degree, if you look. And one can check that here is 2, 0, 2, and 2, like that. So it's different, and this is closely related now to that perverse filtration, perverse grading that we were talking about. And you can see what this is a very special thing. This u, which used to be a degree 2 thing, now it has the same order as this degree 4 thing, and you see why. Because when you delocalize, then here already, sorry, there's also a y, so this is important. This thing has of order y squared, something, remember y was degree 2 chronologically, but perversely now y has degree 4, so this is y squared. Sorry, u becomes y squared. So that means that it doubled its degree compared to the cohomological one. And so that's sort of this delocalization. At some other point, the degrees change, and that's this is perverse pole. So that's one remark. And the other, this last thing, I just want to explain now that if you take this bigrading and you organize your calculation, then finally you have this thing, so let me just write it down one more time. So you have this expression, say y point 2k minus u f hat p hat, and you want to prove that somehow this is some u to some power, and you want to prove that this is 0, right? So you want to prove there exists an f hat such that for every p hat. This is more or less our story. And so the point is that the dimension of the space of f hats is equal to some set A parameterized by pairs of numbers actually, whose number of elements is something like a plus 2 squared over 2, while the dimension of the possible p hats when you do, I mean you just do a linear pair here, is a subset B, whose number of elements is k plus 1 choose 2. So k plus 1 times k over 2. And you can see that this doesn't look very good because this is, maybe I did something wrong. Sorry, this should be 4. I don't know what I did. That should be 4. Yeah, it's like this. Yeah, there's some integral parts. In any case, what is important is that this is order k squared over 4 and this is order k squared over 2. So there's many more p's than f's, so a priori it doesn't look like there should be a solution to this thing, but so amazingly there is. So actually, the fully, it's probably there's a better way, some integral system behind this which explains why there exists an f, such an f hat, which a priori by dimension count should not exist because there is, as I said, twice fewer f hats than p hats. And so the reason, and I'll explain this last thing, I'll just say, the reason for this is the following geometric statement, that if you look at something like this, so it's roughly this, you look for some polynomials pk, which are defined in two variables, so it's a two-variable polynomial, which look as follows: the sum, and so now you look this set of A, which I didn't define, is some integer points in a triangle. So both of these A and these are just integer points, some triangles, but A is twice smaller than B. And then you have some coefficients lambda A that you need to find, and some monomials t to the A. So these are two variables that you want to find. So it's just a two-variable integer coefficient polynomial, depending on that thing k. And what you need is that you want, so you look for this pk satisfying that, so that where these are these elements of the second integer once it's in the plane. So these are this you want this pk to vanish for yeah, I'll write it down again, b1, b2, and b. Roughly, this is so the statement is that if you write down a polynomial and you allow its coefficients to be in somewhere, some certain triangle, so that the number of points where it vanishes is also a triangle like this, then such pk exists. It's some completely elementary thing that you can check. So you can make two-varied polynomials vanish at integer points in the triangle with half as many coefficients as the number of points in the triangle. This is some trivial thing, but that's why this is true. This is how it exists. So this pk exists. That's sort of the solution to the problem finally, except there's a minor thing, but I've said that finally our proof is not totally 100% complete because there is some positivity issue, because what we really do is we also allow a coefficient here when we do this matrix, right? We need to. So there is some little epsilon here, some parameter, and we have to prove that in the relation we find that parameter is not 0. So we need to find some positivity thing which In this particular case, actually, it's pretty involved, but I'm optimistic that we can also find that. But since we're only proving a theorem that's already been proved, so that's it's not as important, but it's also interesting. So there's several interesting things just in other subjects in mathematics around.
I renamed chairman for a moment here. So are there any questions?
You have a question, which is just kind of as a general matter, what are the prospects for putting this in like a very general setting? Because I mean, now we know we have to leave for a minute. It's trying to say that there should be like P equals W type of statements in a more general here.
Right.
So what's the prospect for sort of making this kind of independent of the precise details of the postulate basis?
So that's actually very surprising to me, I have to say. So I don't have this global enough vision, I think, on the subject, because apparently there are several other things. It could be that there is no. In any case, I'm an enumerative geometry, so I'm very interested in enumerative versions of this, and not the technical, recursive versions of this. And it's not 100% clear, I think, that in every case you can smooth things out in such a way that you get this thing. So I'm not really very, very optimistic, but I think what this shows is that it's worth looking for it at least, because it's kind of rewarding. I mean, this whole subject now, it takes off, and then from here it goes into some totally positive matrices and lots of various things. So this becomes linked up with some other things, and I think maybe some physics insights would also appear eventually. I mean, it would clarify somehow the integrable systems that are behind this, but I don't know. I mean, I haven't. But I think it has to be. Certainly this beta pole, this perverse pole is something that's interesting.
Any further questions? So I think we'll speaker now.
We'll start at 3 p.m. with Bruno's talk. So we know it said 3 p.m. So 3 p.m.